make it a start on this bright, beautiful day outside, and we're stuck in a room, okay? So today, I don't know why I chose to call it advanced quantum repeaters, because I think all quantum repeaters are advanced devices, given where we are now. So, but I kind of want to carry on from the kind of material we're dealing with last week about these purified swap repeaters. What I'll say is, remember the lecture notes are up on the website. If I had a look this morning, there's about 5 of the speakers have actually put their notes up. You can download them. There's no encryption on them. Use them as you like. So what do we want to cover today? And I actually have a technical problem for this lecture, okay? This lecture could be 10 minutes long, because everything's obvious, or it could be 4 hours long. Actually, Max did let a secret out this morning. Lunch is not until 1:30. That means technically I have 4.5 hours. I didn't see it in the program, okay? I did not see that there's a break, okay? So, but anyway, today, I just want to come back and discuss some of the limitations of the first generation repeaters, introduce this concept that we came out with a long time ago on the second and third generation repeaters, even before repeaters had been developed in the lab, and then just discuss performance and really some of the issues that we're going to have. First generation repeaters do everything you want. So why do we need to look at anything more, okay? Yeah, if we can build a first generation repeater and you have quantum memories that are hours long, it will do everything you want. You will have generation rates of a hertz on planetary communication. So we will go back to the telegraph stage, okay? Our quantum computers synchronizing between here and the US at microhertz rates by the time we get enough entanglement between the two. So really, I mean, the first generation repeaters have a limitation really on size where they can realistically be used, okay? And within a country, maybe okay at those kind of rates, depending on what you want, an application. So what are the limitations? What's actually causing the problems with these first generation repeaters? And I wish I could put my finger on just one thing, okay? But there's quite a number of them, okay? Entanglement distillation, probabilistic. Scales exponentially with the distance between the repeater nodes. That's always bad. Purification, probabilistic, fails. Entanglement swapping, simply if we're using linear optics and we're not using, and we can't do operations and solid-state, probabilistic. So we've got 3 of our primary operations for quantum repeaters in the first generation that are inherently designed to fail. And most of them fail most of the time. Maybe we can get up to 50%, okay? Maybe a little bit more, but this doesn't sound a good idea. Okay, failure, we just try again. No problem, okay? That's the repeated to success philosophy behind these devices. And in a quantum computer where everything's localized, this is a headache, it hits performance, but we can live with it, okay? The problem we have for communication is distance. And I'm very disappointed in my experimental colleagues, okay? I just want them to break one rule, okay? There's only one small rule I want them to break. The speed of light. If you can make the speed of light faster, then these things become better. But given that the speed of light kind of is one of these constants of nature, okay, we can't do that. And the problem is, every time we have a probabilistic operation that may fail, we're heralding it, but that heralding means we have to send a classical communication. And so the problem is, for entanglement distillation at this top point, you're only sending information between adjacent repeater nodes. Let's say 10, 20, 30, 50 kilometers, okay? But we end up doing purification, entanglement swapping over very long distances. That's not only between what happens on adjacent nodes. That means if this swapping operation here fails, I have to tell everyone between to start again. And those 2 points may now be 1,000 K apart. And in this case, we're only dealing with a linear chain, okay? This is everyone knows everyone, okay? Now think about the case where it's a more general network, okay? Yeah, piece of things together. This person dies, okay? Or it fails. They have to tell this person it failed. But this person up here may have thought, oh, okay, I've done something else. I no longer own this piece of this part of the belt state anymore, okay? I'll pass it to them. They pass it to them. So who knows what? So at what point can we do operations, okay? I would like to actually have my network synchronized on the time between these adjacent nodes. But if I do it on adjacent nodes, and I have a peer here, and I have a peer here, and another peer, do I have to now synchronize on the longer timescales? If you don't synchronize on the longer timescales, and something goes wrong, where you're sending that piece of classical information may be irrelevant to that person at that node anymore. They've got to pass it to someone else, and someone else. And so if you don't synchronize on the slowest operation over the entire network, you end up with a belief propagation problem. Where do I send this information and when? And that means you're sending more and more classical messages. And it's a headache. It really is a headache. If it's a small scale network, you can live with this, okay? So if you're 50 or 100 nodes, yeah, you can live with that. But how many nodes are on the internet today? Any idea? Billion? Yeah, at least. So imagine I've got to send information between 1 billion different devices. Yeah, it's not going to happen, okay? So what this means is that this has issues. Also, I want to point out, when we came to look at purification, the form of the noise is important. If our experimentalists are exceptionally good and they can engineer the system to only end up with a mixture between two belt states, that purifies better than a system where you get white noise. And in the white noise case, what we had was it took 3 rounds of purification to start seeing improvements. 3 rounds means 3 rounds of classical communication. So actually, if I had to say what the fundamental limitation to quantum repeaters is, first generation, it's classical communication. And I did emphasize this in the last lecture, classical communication is slow. Exceptionally slow. It's not the speed of light. One of the assumptions we make when we start thinking about repeater networks, and I see it all over the place, and I've done it myself, is we just say, we're building the quantum infrastructure, okay? We're going to tap into the classical infrastructure to do all the classical communication. I'm saying the classical infrastructure is not fit for purpose for this. I cannot use a TCP IP packet or UDP or anything like that, because for us two talking via 2 laptops, this is going to be 0.1 milliseconds. I could probably throw you a pointer faster than this. And that's inherently the way that classical communication is designed. For the reliability of things like this, we don't have a desperate need for that much higher speeds. But in quantum, 1 millisecond for a memory lifetime is huge, okay? So this purification problem we can partially start overcoming, as I introduced, we can go from the standard 2-qubit purification protocols, we can move to error detection codes, okay? And these error detection codes, it saves time. I mean, you get high quality pairs by using more pairs. It saves time, but still they inherently failed. You're still down to 1 round. Given this, these error detection codes, what can I change? Swapping, okay, if I can move swapping into matter systems, so if I can move from a photonic system into a matter system in ion trap, I can do a CNOT gate. So potentially entangled swapping could be deterministic, okay? Purification is inherently probabilistic. The only way around this is I've got to move to error correction. I really don't like that. Even on quantum computers, we're only seeing error correction just at the break-even point now, okay? But I feel I don't have a choice. So of these 3 operations I had just entanglement distribution, entanglement swapping, and purification. I've got to start replacing them one by one. Let's make the assumption now that entanglement swapping is deterministic. If it's not, improve your system, please. So then I'm left with entanglement distribution and purification. So let's look at replacing purification. The only way is error correction. And this is going to be a little bit basic, but I thought the communications people quite often have not been through error correction because it hasn't been part of our toolbox typically. And I'm going to do this very, very simplistically with hopefully the simplest code because it's the one I understand. So the idea behind error correction, okay, it's the same as in the classical world. By encoding your information into a block, if an error happens, you can decode it. So in the 3-qubit error correction code, I'm going to start with the state alpha 0 plus beta 1. I'm going to encode it. These are codings, just CNOT gates. I'm basically going to create a GHZ-like state, alpha 00 plus beta 111. Okay? It is a GHZ. If alpha equals beta, this is a GHZ state. I'm going to wait. And then I'm going to decode the circuit. And if there was no error, I'm going to get my state alpha 0 plus beta 1 back, okay? So in terms of error correction, I'm doing 2 things wrong to start with, okay? First rule in error correction, never decode. I'm protected in here from a bit flip error. I'm not protected out here. But as an example, it's kind of illustrated to go through this. So what happens if I have an error? So I'm going to come in and I'm just going to flip one of this bit in here. Me being an evil person, as Arthur keeps saying, okay, evil Bill, I'm just going to come into the lab and say, ha, 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 your 0 is now a 1. And so we can follow through. We had the state alpha 00 plus beta 11. I'm just going to come through, do a bit flip here. So I go to alpha 10, alpha 010 plus beta 101. I don't know that error has happened. I may have a suspicion, but I don't know if an error has happened. So what happens is I now come through the decoding circuit. There are these 2 CNOT gates. And what happens is this qubit has started as 0, but when I measure it, it's now a 1. Okay? And this one's still a 0. So I know this qubit has had an error, but the top qubit hasn't. So I don't need to do a correction operation because the top one is still pristine. But if there'd been an error on this top qubit, these measurements would have told me how to correct it. And that really is the premise behind error correction, okay? The problem with this is we're decoding the state. And it really, I just can't emphasize enough. You don't do it. You don't do it in computation, because in computation, I'm looking with error correction to get effective error rates of 10 to minus 15, okay? As soon as I decode, I've now got error rates of 1%. My computation is gone. So what we do is there's a simple way around this. It's still the same encoding circuit, but I just add 2 ancilla qubits. And I kind of measure the parity of these two on here, the parity of this and this on this one, and that parity tells me whether there's been an error or no error, okay? So we can put the error in again. And just give you a second to have a look at it while I drink some Coca-Cola. So what you see, after this error, the second bit has flipped from 1 to 0. Well, it was 0, it's now 1. It was 1, it's now 0. So now at the detection side, at the decoding side, I add 2 ancilla qubits, and I do these C0 gates. And when I do these C0 gates, in this case, this changes, this state at the start of 0 changes to a 1. And when I measure it, 1 and 0, that tells me I've had a bit flip error on the second qubit. It tells me then to come through and physically do a bit flip on that second qubit. If there's an error on this qubit, I end up with a different example down here. And so that for a bit flip on any one of these, on qubit 1 or 2 or 3, I correct that error. The state is not decoded. That's important. But I'm telling you now where the error was, okay? Actually, it doesn't matter. You randomly choose the error is here or here or here, okay? Doesn't matter. There's nothing in the circuit that depends on where the error is. It's general. Now the problem is, what happens if there's 2 errors? Okay? There's an error here and here. What this means is it's like we flipped. Instead of having alpha 0, 0 plus beta 1, 1, it's now like we have alpha 1, 1, 0 plus beta 0, 0, 1. That actually looks like it's an error on the third qubit. This code will correct it to be alpha 1, 1, 1 plus beta 0, 0, 0. Because this code, 3-qubit code, corrects 1 error. 2 errors, it's impossible to correct. The bit flip code is a very nice illustrated code of kind of how error correction works. It is a classical code, okay? The problem is have bit flip errors. So we have both X and Z. Bit flip and sign flip. These happen both. This code only fixes 1. So we need to look at other codes. And one example, and there's a whole lot out there. If you look at some of the posters, we have posters on LDPC codes, there's surface codes. The variety of codes is huge, but all these codes kind of fix general errors, okay? So I just put down some of the simplest one, but the reason I did this, okay, going from here, which looked quite simple, okay, going to the 7-qubit steam code, it looks a little bit more complicated with more gates. And the bigger the code, the more gates you're doing. The more gates you're doing, the more chances of errors in these gates. So there's a trade-off, and all error correction codes have a threshold, okay? And that threshold is important. Some of the earliest error correction codes had thresholds of 10 to minus 7, 10 to minus 8. The surface code is 1.1% or of that kind of order per gate. So we then have a choice. But maybe the thing is, while this may be an interesting or a question about error correction, what does it have to do with communication? Got to check it's okay. Otherwise, the lecture would stop. So really, how does this help in communication, okay? And the answer is actually quite simple. So what we're going to do is we're going to think about an encoding part and a decoding part, but in between the two nodes, we share 3 bell pairs, okay? We share 3 copies of 0, 0 plus 1, 1. So the normal error correction, I created the state, shipped it across the channel, then do the correction. In this case, I create 3 copies. The part analysis side, I do the 3-qubit encoding. On Bob's side, coming back to the no ancilla case, I do the 3-qubit decoding. Encoding on the left, decoding on the right. I now measure these qubits and Alice forwards classical information about what her measurement results were to Bob. And I've looked at ideal case here. There's 3 copies of the state, just in terms of a very bad notation, but it kind of sees what's going on coming through all these gates. When we measure qubits 3, 4, and 5, or 3, 4, 5, and 6, we end up with a state here, 0, 0 plus 1, 1. Not unexpected, because that's what we started with. Now, what happens when we have an error? And I decided this time to be nasty to myself. I put the error on the first qubit, okay? We can go through the same process, but now writing the 8 potential states out here, okay? 0, 1, this. I can come through the C0 gates and the C0 gates to end up here. But then I measure qubits 3, 4, 5, and 6. So I measure this, 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 and this. And I end up with patterns, and it's worthwhile just coming back. That typically when what's wrong, my slides look too similar. Typically when I measure in these bases here, I end up with 1 of 4 states. 0, 0, 0, 1, 1, 1, or 1, 1, 0, 0, 0, 0, 1, 1. So there's 4 possible measurement results that come out of this. In this case, when I do these measurements, I end up with getting measurement results 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0. These results are completely different than the case with no error, okay? It's a unique pattern. And given that pattern, it tells me to do an X correction on the first qubit. but we should not decode. So in this case, we're doing what we shouldn't. We're removing our error correction. We shouldn't do that. So I can do the same circuit, add ancillaries here, add ancillaries here. Run the circuit the same way you are before, communicate the results of these. But now what happens, okay, you don't get a state 0, 0 plus 1, 1 being shared. The state you get up here is kind of like 0, 0, 0 for Alice, 0, 0, 0 for Bob, 1, 1, 1 for Alice, 1, 1, 1 for Bob. So you get a logically encoded state. Ironically, which is a G shed state in this case. So why is this important? Because what this means is now is that we have some redundancy in this. Again, I've used the 3-qubit code just for illustrative examples. You can replace this with whatever code you want. Okay. I do need to take a step back. I say you should never decode, okay? That's the rule in error correction. Does it apply in communication? In computation, I don't want to decode because I'm going to be running a computation with 10 to the 12 gates and various things like this, okay? So decoding suddenly means an error has happened. In communication, decode or not decode, it depends. Good practice should be you don't decode, okay? But if I'm doing a task where it doesn't matter too much, okay, then I'm going to introduce a 1% error, maybe for QKD, I can live with it. If I'm trying to do distributed computation where I need to use these things, then no. So really, you need to think about this from the application. Also, one of the things that's probably going to happen is in the early days in communication, we're going to be qubit limited, okay? I need 5 qubits and 5 qubits for the simplest demonstration of this. Here I only need 6. So the question is, what do we do going along to this? So one thing that we need to think about, again, here I'm always talking about feeding classical information, but typically this classical information is being fed just one way from Alice to Bob. Bob does not have to feed their information to Alice. Why can't Alice just take her syndrome measurement results and correct her state, and Bob do his ones and correct results, and remove the classical communication? That would be nice, correct? We do have some fantasies, okay? But no, can't remove it. If you look, there's certain cases, if you look through all the potential syndromes, there's normally 1 or 2 where the results from here need to be combined with the results from here to say what the correction operation is. So I'm always going to have one-way communication. The question is, in this particular case here, the correction operation really, if there's an error, tells Bob to bit flip all his bits or something like this, okay? When do I need to do that correction? So we have a thing called the Pauly frame, okay? Which was used, it's used in, yep. There's a mic here, please come and grab it. No, I will come and bring it. Thank you for the break. I can finish some Coke.
So when you measure the syndrome Alice, the syndrome from Alice, why can't you already correct the code from Alice's side and you have to feed forward to Bob? I don't understand.
So typically you only have to correct one side, okay? So typically at the moment, what happens when you look at some of the syndromes, there are some syndromes where it's a joint error, okay? So there's a possibility that what happens is that the syndrome says that there has been an error, okay? There's been an X error. Your measurement on Alice's side says, yes, there was an X error. Do an X, so Alice does an X correction, okay? Bob's syndrome measurement says there was an X error. Bob does syndrome. Both of them do X's to a bell state. They cancel each other out.
So why don't they just say like Bob does the error correction and Alice doesn't do anything?
Because there's a possibility that in some of the cases that Alice doesn't have. What happens? This is the bit flip code, okay?
Right.
Which is a code. But let's say hypothetically Alice had lost her qubit. So Alice's qubit, I just decided, yeah, no, I'm taking that. Thank you, it's mine. So I mean, the bit flip code is very special in a sense. But when you do the bigger codes, there's a possibility that you can get an error on Alice's side that doesn't affect Bob. So Alice can do some corrections herself, but it depends on where things are. And the bit flip code is not required, but generally it is.
Okay, thank you.
I need a chair.
I just wanted to ask, this looked really nice for bit flip or qubit flip, but does this kind of error correction work for like in a more general case, in the sense that, you know, when you send, I'm just thinking about photonics, when you send your photons through, I don't know, free space or whatever, there is always this drift phase that is going on. So I was wondering if these error corrections could work in this drift phase correction kind of thing.
We better hope they do. The problem is, if I like this chair, if I fall off, you've got to take over the lecture, okay? So the problem at the moment is, if we can't do error correction in photonics, okay, so the first thing is, all photonic quantum computation, okay, is based on error correction. So basically there, within the lab, we're seeing good promise that these things work. So the question is, can it happen in free space in the fibers? If it can't, we have a problem, okay? What that means is that the second and third generation repeaters functionally will not work. Therefore, the only way to go from a first generation repeater that's operating at hertz rates over 1000K to a megahertz rate is to make 1 million copies of them. Is to really paralyze the system up in a sense. And later on, I'll show you the scaling for these different repeaters. And the first generation are kind of frightening in a sense. So, I mean, error correction imposes a fundamental limit. In the purification case, or in entanglement distribution, if my photon gets through 1% of the time, I can still use it. The purification codes that I wrote down work in the previous lecture, have the success probability and the fidelity bounded at 50%. So as long as you're above 50%, you gain. The problem with the error correction, okay, all errors you've had here, all errors you have in these gates, added up, has to be less than 50%. So sum all the errors together, okay, roughly, and the errors have to be less than that. Why? Why is there a fundamental limit of 50%? I wish there wasn't, okay? But it's a fundamental limit due to no cloning. E.g., if I only had if I had these errors, and I give the state to my friend here, And unfortunately, you have 66% errors, okay? But I've been evil and I've got that 66%. I can recover it, okay? I can get a signal back. If you can get a signal back, we're cloned. No cloning is fundamental. So therefore, in error correction codes, there's a fundamental limit for general errors at 50%. Lost codes exceed this with classical communication, where you can herald, okay? But normally for most error correction, we want to stay at codes less than 50%. And actually, we want to stay much less than 50%. So for the surface code, okay, which is one of the ones I mentioned, I want the error for these gates to be of order 1%. 1% is the threshold where things start breaking down. So that's kind of what you have to live with. I mean, can we do it? We have some young minds in this room. That's your challenge. You're in this field. So the question really is, how do we push the boundaries? So one, we need the experimenters to decrease the errors, okay, in the apparatus, but we also need the theorists to come up with better and better schemes, okay? And then hopefully we can meet in the middle somewhere and these things work. But if we don't get error correction working, I'll be provocative. I don't know whether we'll have a quantum internet. Or no, I'll be slightly more optimistic. I don't think we'll have a useful quantum internet. And one of the reasons is that I could probably still use these things for QKD, but I couldn't use this for other applications. So that's one of the headaches. I mean, we're too early, in a sense. We had similar issues in quantum computation, and it took us 20 years to actually start showing the error correction is now an advantage, okay? 20 years. We had a lot of these error correction codes around 2000. We've seen a number of the very big groups like Google, IBM, and various other groups now showing error correction working over multiple time steps. 25 years later. But one of the reasons we talk about generation of repeaters is obviously we can't start with error correction to start with, okay? That's unrealistic. I'd like to, but that's not where we are. So we've got to build along the way.
Hello? Right. So a different question. When you measure the syndromes on the ancilla qubits, how do you make sure that there's no error occurring on that ancilla qubit? Like say if you measure the syndrome and then you have a 1 and then it flipped and then it becomes a 0 again. Good question. And the answer is these better be good qubits. And no, and actually I'm being flippant here, but I mean, no, the question you've raised is true in all error correction. These qubits do introduce errors, okay? Then if these were whoops. If these were bad qubits, but these were good qubits, then the first thing I would do is give up the bad qubits and use the good qubits. So what I need to do is that typically we assume that these qubits and these qubits both have errors, okay? And so when we talk about what the degree of errors is, we have to take into account that everything's noisy. And so what that means is, and it's one of the headaches, okay? So if I come back a slide, okay? In this case here, okay? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 operations involving ancillas, okay? Now,
let's say there's no error, okay? This was perfect, okay? If each one of these has an error rate epsilon, then after I do this, I'm going to have an error rate, a fidelity of the recording state, 1 minus 12 epsilon. Because these will induce errors. I can't avoid it. So the question that you always come to these codes is how much of an error are they introducing? And there's a trade-off. At the moment, let's say hypothetically, the chance of getting this qubit through, okay, you can set it to me with a 99% fidelity, okay? Now let's say that my gates here have a good qubits, good gates, point error rate, okay? Do I do error correction or do I not do error correction? 1 minus 12 times 0.001, 12 times 0.001 is greater than 1%. So I don't do it. And so that's one of the considerations you always have to think about in a sense, okay? But if my pair that I was sharing to you was only 95%, again, so there's always, that's what I'm saying, there's always a threshold where you make the decision. So just doing error correction because you have noisy gates, you have to think how noisy, because those gates may bring in more noise than you fix. More questions? More Coke? See, today I'm in the position of power. No chairman. So I'm speaker and chairman, or chairperson. Very dangerous. So I just want to kind of run you through, I mean, and these kind of, this is in the notes that you can find online, but what happens with that when there's a random error, okay? And just coming through this bit for code, okay? I would say that there's a probability P that a bit flip occurs on one of these ones, okay? And then we can express our total state in this kind of form. We can go through do the error correction. If you want homework, I'm told I should give you homework. Show it for yourselves, or believe me. But what happens is that if the gates are perfect, you'll end up with a state that comes out here that looks very much like this, but P has been changed to P dash, and now P dash is 3P squared minus 2P cubed. And so basically, as long as P is less than a half, I didn't tell you the error rate had to be less than 50%, then P dash is less than P. So we can look at the fidelity, your initial fidelity, and the final fidelity afterwards. And what you see is your fidelity has gone up, just like we saw in the purification case, okay? So if the local error gate is small enough, this does work. The 3-qubit code, bit flips, unrealistic, of course. You can move to the 5-qubit code, okay? And ironically, you may find this surprising. The work has been published, but this is a PhD thesis out of Munich in 2004. Very ahead of their time in a sense, okay? And again, it's the same kind of structure, okay? Share 5 bell pairs, do all the gates, the measurements, and here I'm very explicit. the maximum fidelity after this is 1 minus 2n times the gate area. And in this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 1 minus 26 times the gate error rate. The gate error rate needs to be pretty good for using a code like this, okay? And that's the threshold for these kind of codes. If I replace this with the surface code or one of the low density parity codes, then I can get away with having error rates of 0.1% because of the way the codes work. So there's a big trade-off in what code should we use, okay, in communication. I don't know. Your code choice depends upon your physical system. As theorists, we kind of like choosing arbitrary codes, but in a sense, we will need to tailor the error correction codes we're using to the physical system because the physical system will have biased noise. So we won't have white noise. The probability of an X error and a Z error will not be the same. You say, oh, does it matter? Yes, if you can give me a bias, okay. If you tell me that the bit flip error is 100 times less than the Z error, I can build a code where I can really exploit that. And the surface code, for instance, when we played with that in the early days, you take the threshold at that stage from 0.8 to 1.2, okay? That gap is quite important, okay? So these are the components. This is potentially how error correction works. I think we should take a break for 5 minutes. So let's take a 5-minute break, pit stop, coffee. Okay, it's probably time to make a start again. So the fundamental question here is, given this error correction across distributed bell pairs, how does it help, okay? That's a fundamental question. And this is very, very old. What I say is, this is old work, because you see the date that I put down here, 2009. From Liang Zhang and some of his colleagues, including myself, Rob and Kai. So what we want to, I just kind of want to show you what we kind of do here to start with, okay? And there's many ways to do it. I've done the error correction in the simplest way, but what we're going to do here is we're going to assume that I have blue qubits and grey qubits, okay? It's just for convenience. The blue qubits are just going to be qubits within my device that I can create logical states on. So I can create superpositions like 0, 0, 0 plus 1, 1, 1. The grey qubits are basically qubits that are going to be tailored for emitting photons to do communication. So what we're going to do to start with in step 1 is I'm going to create a logical plus state. The 3 qubits, 0, 0, 0 plus 1, 1, 1. On Alice's side, on Bob's side, Bob has it easy. Bob just has to create the logical 0 state, 0, 0, 0. Once that's been achieved, the next step is Alice and Bob, using the grey qubits, share 3 noisy bell pairs. I should say noisy, 3 bell pairs. And then, basically, they do an operation up here, which is basically a teleportation-like operation, okay? To kind of entangle this with this with this, and kind of remove these pairs from the center and create the state 0, 0 plus 1, 1. This is effectively a C-not gate. We'll go through this in detail, but this is kind of a way that creates a logical bell state in a reliable fashion. So we need some details, okay? And basically, it's worth coming back. Given I had these 3 bell pairs, okay? What's my gate operation? Basically, all I need to do, in a sense, is entangle and then measure the grey qubit in an appropriate basis. The whole point is that once I've done that, once I have this logical bell pair between Alice and Bob, I can do the same between Bob and Charlie, Charlie and David. These are logical forms, so I can now do logical entanglement swapping gates. So I move from physical entanglement swapping to logical gates. And so then what I can do, in a sense, is now start creating entanglement instead of between here and here, and entanglement, logical entanglement between here and here. I can now go from here to here, all in an error-corrected logical form. And the key is, when I do this, there is information from these bell measurements, but I see this is the Pauli frame, and it brings me back to this Pauli frame thing that we kind of got slightly distracted from, okay? So with the Pauli frame, I need to make a decision about when I do the correction operation, okay? I don't need to do it immediately. I can hold off, because let's say I give you an X operation to do now, okay? You keep in your state. A second later, I give you another X operation. If you had corrected the first X, when I give you the second one, you have to do it again, correct? But if you hadn't done it and I gave you an X, and I gave you an X, you'd say, aha, X squared equals identity, you do nothing. So one of the things about the Pauli frame is, rather than, I can say the operations are X, X, Z, Z, Y, X, Z, and there's a whole sequence of these things along. At the end, do I do them individually, or do I just work out what the net gate is? And that net gate is a Pauli frame. It means that rather than having to do 50 or 100 gates, I just have to do one. But the key thing is I need to do that correction operation before I do a non-Clifford gate. So if I'm in a quantum computer, I can do C-not gates, Hadamard, the Clifford gates easily. But if I'm going to do a T gate, a pi over 8 gate, I've got to do that correction first, because this Pauli frame obviously commutes with all the Pauli gate operations, but the T gate's not Pauli. So if you don't correct it and you do it, you'll end up, your computation will start going wrong. Actually, depending on your application, we don't use T gates that often in communication. We use them a lot in computation. So the sheer fact is that once you have this, and here I'll be kind of agnostic about what the code is. I haven't told you the code, okay? I'm just saying, we create a logical state. Maybe this is 3 qubits. Maybe this is 5 qubits. Maybe this is 100 qubits. But once I have this, I can actually start looking at some of the property of these, okay? And so that I kind of want to go here through a number of these and look at some of the resources. So write down the error correction code in this normal convention, the resources, the number of qubits per station, okay? There's no universal measure, but it's one that we can think about. And the distance that you get, that you can communicate across before you lose entanglement, say. So no encoding, with the numbers that I'm running here with error rates of about 0.3%, initial fidelity of 95%, a distance between repeater nodes of 10K. With no encoding, I get to about 180 kilometers before goodbye. Remarkably, the 3-qubit code gives me about it's pretty good. The 5-qubit is even better. But you start looking at some of the better codes, okay? The quantum Reed-Solomon code. Ridiculous. Okay? That's a distance before. So if you get a code in this 103.119 code, you can communicate across the planet. What I haven't told you here is what the resources per qubit was, because I could not work the numbers out easily, but the Bacon-Shaw code is 42 qubits per station. So these are not, when you're involving everything, these are no longer small devices, okay? 40 qubits may not sound much in computation, okay? But in communication, it's a lot. But this kind of gives you the hint that we're going to be forced to go to error correction in a sense, if we want large distances. So just plotting this a different way, okay? What happens with the error probability Q, okay? Versus this maximum distance, okay? So going from 0.3% to 5%. You can see what's happening to the different codes. And the performance drops remarkably fast with the error rate. So the quantum Reed-Solomon code goes from 10 to the 10 and triple its error rate, and I've lost 6 orders of magnitude in terms of the distance. And you know, some of these codes cross each other. It's all about the properties that are going on in a sense, okay? So the point for this diagram is, okay, we probably can't afford to live with error rates much greater than 1%, even in communication. Sorry. Error correction for quantum communication still is going to be as stringent as it is in computation. We're just going to be able to use smaller codes, but we're not going to be able to suddenly say that we can use higher error rates. There is a problem here, okay? And I've been glossing over something. And I always like glossing over things. Please, there's a mic somewhere. I have it.
Looking at that table you showed me about the distance and the amount of qubits per stations, to achieve this distance, how many stations? How far away is
There's
this
a station every 10 kilometers.
Oh, okay. I'm sorry, I missed that.
Yeah, no, sorry, I should have explained. So actually, to go a distance of 10 to 11, that's a lot of stations. Okay. So one thing that I've glossed over, okay, and we tend to do it all the time in repeaters, okay? I'm kind of doing all my, when I put this up, I was kind of doing all my operations in parallel, okay? When I do all my operations in parallel, that's a real headache for classical communication. It also means that if I've got to wait for the signals from this middle node to arrive here, these probably have to have very, very good memories. So there's one of the tricks. Why do we always think about doing communication, every operation at the same time? When you see quantum repeaters drawn on paper, we put all the repeaters down, we do purification, swapping, everything is done simultaneously. Why?
Because we don't have memory.
If they don't have memories, or actually for QKD, which is where some of the early ideas were, it doesn't matter what happens at these endpoint nodes. So if you're gonna, if you're not worried about if the end nodes now have infinite length memories, this doesn't matter. We can wait for the classical communication, okay? But the reason I object to it personally, what's an end node? We said there are a billion items on the internet now. That means all billion of those are going to have long-lived quantum memories. So what has to happen is that thinking that a repeater is not going to be where a user is not thinking, is you need to think more. So one of the tricks you can do with these second generation repeaters, is to do a transmission scheme, and this could be to generate entanglement if you wanted. But what can happen is that Alice establishes a link to Bob and then sends back classical information to the standard entanglement distribution. As this is being established, we just do it hop by hop by hop. And the advantage of doing it hop by hop is that you can send all the results from these Bell state measurements and the entanglement swapping on the next classical signal that goes down. They pick them up and they just concatenate them all together. So this kind of left to right scheme means that actually, in this case, the left-hand side would need a long-lived memory. The right-hand side doesn't. The right-hand side gets the results one cycle later. And we know that this kind of time is not going to be hours and minutes because it's just the distance between two repeater nodes. So when you start thinking about design, don't only think about design for how the quantum communication, how the quantum side goes. Think about where your classical information is going at the same time. So now repeaters, some characterizations. Again, this is a table that I took from one of Liang Zhang's papers and how we characterize the 3 generation of repeaters, okay? To do this characterization, I'm going to separate errors into 2, okay? I'm going to talk about loss errors, photons being absorbed in the channel, okay? In most communications, that's the most severe error type, okay? And then operational errors, okay? And operational errors are my C0 gate didn't actually do a real C0 gate, or my bit flip was only 99% of bit flip. These operational errors are kind of where the previous error correction second generation came in. When I want to deal with loss errors, there are 2 ways, okay? Maybe there's a third that I haven't thought about or ever thought about. The first one is just do entanglement, your standard conventional entanglement distribution where you hear the result, communicate back where it fails or not. There's many names for this, but this is heralded entanglement generation, entanglement distribution. The other way, okay, that's the way I like conceptually, is take your information and code it into an error correction code that handles loss and then ship it between nodes. And that's quantum error correction for loss. Easy, hard. Oh no, let me say this. Easy, exceptionally hard. Who has the mic? I mean, this lecture, you've got to get exercise.
So, what this entanglement generation is a probabilistic, like by nature. So when you do error correction, so you repeat until you succeed.
So that works first time. So so this one is probabilistic. This one is deterministic. And that raises the point that I wanted to say. So given that discussion we had about 50% errors, so with Hilton entanglement distribution, my repeater stations can be an arbitrary distance apart, okay? Could be 1 meter, could be 1,000 K. You choose it and your performance does it. When it comes down to quantum error correction, including all the loss events over the time within the repeater node, within the channel, at the other repeater node, all those losses have to be less than 50%. So coupling from your quantum to your fiber, which we normally talk about in the dB term, okay? Suddenly we have to get these numbers down at 0.1 dB. So what I'm saying is the coupling efficiencies are extremely hard, and we're not there yet. So that's kind of why the third generation repeaters, from that point of view, we just don't see them in a sense. The mic, yep. Yep.
So for the second one, do you need a quantum repeater station every 10 kilometers or so? Because fiber is 0.2 dB per kilometer, right?
Yeah,
so
so
if you only
50% is roughly
3 dB.
Yeah, 3 dB is roughly 17.1 kilometers, if I remember right, or something like this. So yeah, you need the repeater stations have a maximum distance of that, okay? And actually, do I want to operate at that 50% mark? No way. So most of these these codes based, these repeater schemes based on loss-based error correction, maybe the repeater stations are only 5K apart.
Okay, so in that case, with that scheme, you can have probably a cluster of quantum computers communicating within one city, but intercity is just impossible, basically.
Let's discuss this on the next slide.
Okay.
Because that's one of the big things that we're going to get into here, okay? So that's a way that we characterize loss errors, okay? Operational errors, we've got purification, and then we have error correction. So error detection, error correction. And the way we characterize the generation of repeaters is very simple, okay? First generation, herald entanglement generation, and purification. Second generation, herald entanglement generation, and error correction. Third generation, error correction and error correction. So, simple, first generation. Hard, third generation. And there's a big jump going from first to even second, okay? So what I wanted to is just bring up the part of one of the slides in terms of talking about entanglement costs and various things of this, and to start coming back to answer your question in a sense, okay? So just thinking about which way we're doing things, which is what this table does, we want to look at two things, okay? The characteristic time that we need on the network, okay? And then the first generation repeaters, it really is, or the characteristic distance is really the distance of the entire network. The memories and that all have to be long-lived compared to the distance that you're doing and the number of round-trip times that you're doing over that, okay? The second generation are now just basically what's between two adjacent repeater nodes. The third generation isn't distance dependent at all anymore. It depends on how fast you can do operations within your repeater node. So whether the repeater stations are 1K apart, 4K apart, it doesn't care. It only says, what is this time to do gate operations? Then we need to think about cost. This is kind of where things become frightening in a sense, okay? And this is a cost coefficient. It's an arbitrary metric. We want to say, as we increase the distance, how do the resources scale? The first generation, poly of the total distance, poly log total. I don't like polynomials, okay? Really, really, really bad. What that means is that almost no scheme scales linearly. Some schemes may be L to the 1.5. I've seen L squared. I've seen L cubed. The second generation, polylog. The third generation, polylog, okay? And so you suddenly see now there's a huge resource differential between the first generation and the second and third. What's causing that difference? Error correction. If you look at the scaling on error correction, almost all good error correction schemes scale as polylog. The first generation doesn't. So now the question is, and it's one that we needed to come back to here, is your repeater stations can we live them being 4K apart? I'll ask you a question then, okay? I'll rephrase this because I like being provocative, okay? So the question is, at 4K per repeater node, I will give you a gigahertz rate, okay? And that's the premise that the third generation repeaters should be able to start giving you a gigahertz rate of distributing entanglement between two parties, okay, over long distances. The second generation, I will give you kilohertz. 3 to 6 orders of magnitude, okay? So is that is having your repeater stations at longer distances worth that performance hit? Do you want to have 1,000 times the parallel equipment sitting in your device? I'm not saying what the right answer is, but I mean, these are kind of the questions we have to ask. And then if you come to here, hertz, okay? So that's kind of why we say rate of order hertz, kilohertz. I mean, I can probably get this up into a high kilohertz, okay? But gigahertz, okay? But gigahertz, but 4K. And I've seen papers where people have distances running between 100 meters and 8 or 9 kilometers, okay? I don't like 4K. What do I do about it? Any solutions? Why use telecom fiber? I mean, if we're building a special infrastructure, there are new low loss fibers coming out that have double the attenuation length. So if I can suddenly go from 4K or 8K to 10 or 12, that's any more plausible, okay? I think the best I saw a while ago was chalcogenide fibers, okay, which are a really unusual fiber thing, built in a low G environment, okay, had, if I remember the numbers, it was 0.001 dB per kilometer, okay? The maximum length they produced was something like 30 centimeters. But what I'm saying is at the moment, there's a lot of work going on to changing, to trying to improve fibers at the moment. Given this doesn't have to be done tomorrow, it's possible at the moment, just putting in modern fibers where we get double the distance, going from 8 to 16, actually in the real world, lots of repeater stations of that are, depending on the situation, sit between about 20 and 40K apart. We don't have very many links at 100 without wasting lots and lots of energy, okay? So where the magic number is, I don't know, but the question is, what do you want to do with it? Do you want performance? That's the headache. And it's one kind of unique to quantum, because classical, I don't have it. Is there an incentive for me classically to get better, a lot more, to use low loss fibers? Actually, yes, because in the classical world, I'm trying to, I mean, one of the trends you would never hear about it, but we're trying to use weaker and weaker signals coming through the fibers. So it used to be we pumped lots of power through, now we're trying to decrease the energy consumption. So actually decreasing the loss helps energy budgets. So really, this kind of gives you an indication of what's happening with the first, second, and third generation repeaters. So before I finish, I've got a few more slides left here, but the first generation is really where we have to be focused now in terms of the labs, okay?
These rates you have told about these repeaters by generation, these are not for the dark fiber. This is for normal fiber that use.
What do you mean, the new fibers?
Because you said that there's low loss fiber. I think so that's dark fiber.
It's dark fibers at the moment. It's just because some of it's used actively. So what it comes down to is many companies are just placing new fiber in, and they become live as time goes on. Okay, so I mean, but we're starting to run out of dark fiber.
But these rates and these all calculations that we have seen in this is based on dark fiber or the normal fiber that.
So what I'm saying is the fibers here they are normal telecom fiber, but when I say normal telecom fiber, they may be dark, they may not be dark, okay? So the difference with dark fibers normally a bundle that just is not being used in a sense, and as researchers, we tend to get used to them, to do them. Actually, we have a bit of dark fiber between here and the mainland that we can use for certain experiments at certain times, okay? Because we're a nice 300 or 400, nice 500 kilometers away from the mainland. So it's not a waste, but there's been QKD experiments over those kind of links, okay? Because it's a very nice underwater test bed, okay? But I mean, in the end, dark fibers do not stay dark. What happens is that we invest, you put dark fibers in, and then we start selling the dark fibers off to real users in a sense. And so they very quickly disappear. What was dark now is no longer dark, maybe 6 or 9 months down the track. But you kind of see the trade-off we're seeing here. First generation repeaters, we have a lot of the components sitting in the labs already, okay? So we have the fibers, we have single photon sources, the quantum dots. We have memories, NV centers, ensembles of rubidium atoms. But we haven't really demonstrated all of these things together in a sense, okay? Even for the first generation, and it's because it's hard. It really is, these are really hard experiments because what's one of the biggest problems? Interfacing a photon, reading a photon in and out of a memory, okay? Purification was shown 20 years ago, all photonics, in a heralded fashion. But when we want to start doing this, we really just, as a community, this is a lot of hard engineering. Most groups, I mean, if I want to do a Bell state measurement, I take 3 quantum dots. I want Jackie's 99.5 Hong Mandel dip, okay? it's all a challenge, okay? So, and this is kind of why this first generation is what we're working on. But the thing that I'm afraid of, we don't want to take this to extremes. This is probably useful within cities or between close cities in a sense, okay? Having a rate of a hertz over 1,000 kilometers, it's like twin field QKD is being demonstrated over 1,200 kilometers, okay? But the rate's really low. Do I want a few bits per second? It's the same as repeater context. So what's going to have to happen is we're going to have to show a lot of these elements and then slowly migrate to the second generation. And the second generation means that within these matter memories, within these matter repeater stations, we're going to have to start doing gates. So when you choose your memory, okay, if it's an ensemble memory, how do I have two excitations sitting within an ensemble of gases? How do I do a CNOT gate between them? If it's an NV center, and I can write into the electron spin and a few nuclear spins, then there's a way that I can potentially do quantum gates sitting in there, okay? So your physical system here kind of affects how you go from here to here. What's the best? I don't know. I mean, I'm still, it's an ongoing problem in a sense. So it's an ongoing challenge to just work out what's more. But then when we really come from second to third, we really have to engineer the losses in the fiber, the coupling from your memory to the fiber. That has become low. Am I pessimistic about that? No, because what have I seen recently, okay? Who here's an experimentalist? Do you use single photon, single photon detectors? What's your coupling efficiency? System efficiency? 80?
If you use NSPDs, like,
Yeah.
if they are fiber coupled, like 90-something%.
Yeah, so some of the companies like PsiQuantum now are 99.6. Okay? These are not what we commercially have, but the reason I want to mention those kind of numbers, what we can buy is this. But some of the companies are now been spending a lot of time really engineering those interfaces. 99.6 starts being useful here, correct? If it's not an SSPD, but it's memory sitting in there, the numbers are getting into the kind of ballpark where I can think, yes, there's some hope. I mean, I know the PsiQuantum folk, this is not a physics problem. They spend a lot of time engineering, okay? It's just tough, it's tough work. So I want to point one or two things out about these third generation repeaters, okay? Unfortunately, the first thing is loss and general errors are not independent of one another. So I take an example from Tom Stace and some old colleagues where I looked at the two different errors, okay? So given that I can't read that, I still can't read that, okay? But the x-axis is the loss, okay? So the x-axis is loss going between 0 and 50%. And this is the amount of general errors that I can handle. And I have to live within this gray area. So the more loss you have, the less general errors I can have. So there's a trade-off. So that, in this particular figure, and this is the absolute boundary, okay? At this particular boundary, what happens is that it's a threshold, and the threshold you never want to work at. The threshold is where the resource goes from being infinite to being polynomial, okay? I want to work at least an order of magnitude below that. So I'm going to want to be working here. And that's kind of where you're going to be wanting to look in the third generation repeaters at probably operational errors of maybe 0.1% and probably loss errors of less than 10%, maybe 20%. I mean, but once we have that, then one of the things that when we think about the first generation repeaters, okay, they are scheme to do entanglement distribution. They have to create an entangled pair between two arbitrary points. When you move to third generation and second generation, do I have to encode half a bell pair here? I can just encode, given it's loss protected in third generation, I've got error correction versus loss and operational errors. I can just encode alpha and beta in a logical state and ship it down the line with the classical messaging at the same time, so that Bob receives the logically encoded state. The reason the rates are so fast is because once Alice has shipped her message, okay, Alice ships a message in a nanosecond. She's free. She now ship the next one. What's the problem with this? Security? Is there any security? Alice, Bob, Evil Bill. I own the telecom infrastructure in between. Thank you very much for all your data. So the reason I wanted to emphasize this is because that when we think about designing these things, quite often we wave our hands to start with and say, oh, quantum, communication, security is built in. Here is a practical example where it's not. Can I build security into this? Yes, I know how. We can chat about it afterwards, but it's an add-on. It's not done at the lower levels in a sense. I can take the same scheme and do it in what we called a butterfly many years ago, where I have some more central node and they kind of ship half a bell pair out each, so that these error corrected bell pairs receive at Alice and Bob at roughly the same time. And what that means is no repeater station along here needs any long-lived memories at all, including all the classical information flow. So you can start thinking about the design of this. If you were to do this, and I put this up in this small figure here, we call it a butterfly. If you wanted to do it flat, which is the typical way that we think about it, the poorly framed information, I've still got to ship. And that's a green line, so that these end two memories have to wait until the signals arrive. If this is over 1000K, they're now waiting microseconds, so therefore Alice and Bob have to have quantum memories. In this particular scheme here, the classical information flows exactly at the same time the quantum signals are coming down. No memories are required. You may think, okay, does it matter? Actually, the reason I think it does matter about designing where these things are is because in a network, who is the Alice, who is Bob? Do I want to put a memory into every single user? Is every single node now going to have to have long-lived quantum memories? Maybe that's a design consideration you want. But I'm saying here is a potential way around it. Okay, so everything we've talked about so far is really all photonic, is basically using memories and racings of this. We can, of course, and I'm not going to cover this because Coach Jasper did this on the first day here, but we can think about these all photonic repeater schemes, okay? No memories required, just single photon sources, just detectors, build cluster states. Proof of principle is very much been demonstrated. What type of repeater is it? Is it first generation, second generation, third generation? That's a question for you. Who thinks first generation? Put your hands up if you think first generation. One. Second generation? Third generation? Most people are asleep. Sorry?
No memories, I think no third as memory, so first or second.
The problem was why this one is confusing, okay, is the way that this all-photonic scheme was initially proposed, and let me skip back one slide. So this third generation repeater scheme here, these resources, I send them down, Alice and Bob can use them instantly. The next resource appears a nanosecond later. If you think about this inset, this waiting time. So this scheme that Asma originally came up with, they have to wait for all the classical messaging to get to the two end nodes. So they can't repeat every nanosecond. So this can be changed to a third generation repeater scheme, but at the moment it's functioning more as a second generation repeater scheme. Or potentially even as a first generation repeater scheme. And so that's why when we say the second and third generations offer better performance, they only have better performance if you design the system to tailor the classical communication and everything along the way. I can have a third generation repeater and act like this, okay? And then I'm at a first generation repeater, potentially, okay? I have to wait for communication over half the distance of the network. Some notation I just want to come back to because I was asked. From the classical world, a repeater is an electronic device that receives a signal and retransmits it, okay? In the classical world, we have made a very big point of distinguishing all photonic repeaters from the ones with electro-optic devices. It's been done for a very specific reason and various things like this, that we want to try and keep signals in light if we can. So in the classical world, we call these regenerators. And we have the 1R regenerators, which is just reamplification. We have the 2R regenerators, which is reamplification and reshaping, okay? So what happens is it brings the pulse shape back. Your pulse shape is being slightly distorted, you reshape it back. And we have the 3R regenerators, which is reamplification, reshaping, and retiming, resynchronization. So the question we have to start asking, when we think about all photonic repeaters, should we be calling them all photonic repeaters, or should they be all photonic quantum regenerators? you may think there's no, what's the issue here, okay? But the issue is really these repeaters, these quantum repeaters, these quantum devices are going to be part of a network run by engineers and various things like this. Notation has to be consistent along the way, otherwise someone's going to say, oh, replace that repeater, okay? And they put the wrong device in or something like this. I'm not saying what the correct answer is, but I've been talking lots with people like Jeff Shapiro is very passionate about this notation because if we don't fix it now, there'll end up being a whole series of confusion. And it's kind of why in my first lecture, when we talked about repeaterless, okay, there was confusion in the community about what repeaterless meant. And David and I have it because we come from two different communities. If you think about the engineering compared to information theory, correct? The terminology is used differently in a sense. But to me, because I have spent so much time in the telecom world, I think about repeaters as basically reamplification, reshaping. Okay, so I think about them correcting, making resources scale whole number. So no solution, but just think about this, and then when you start writing papers, be very careful with notation, because you will find that you will start moving papers from physical review to IEEE to ACM, and the reviewing community is getting broader. You'll find series of confusion there. And I think we should have a coffee break. Thank you.